Hello, I'm Carl Nelson from the University of Nebraska-Lincoln, and I'll be presenting Kirigami-based disposable laparoscopic instruments under direct surgeon control. The problem that we're addressing has to do with the rigid, straight nature of most laparoscopic instruments, and this can be a constraint to accessing certain surgical sites. Recognizing this limitation, some robotic articulated instruments have been developed that spread those articulations across the length of the shaft of the tool. But in the space of manually operated instruments, we don't usually see this. We see articulation concentrated at the tip of the tool just to orient the tip, but this still presents a limitation for accessing certain surgical sites. The reason for this limitation in the manual tool space is mainly due to the difficulty of designing input mapping mechanisms through which a user can intuitively operate the instrument. So our goal is to overcome some of these barriers at low cost, developing simple, inexpensive manual instruments with distributed articulation. The approach that we take is based on principles of Japanese paper cutting and folding, so kirigami or origami, and this allows us to use standard processes like laser cutting in planar materials such as heavy paper or plastic sheets to create three-dimensional objects out of a two-dimensional workpiece. So a subset of fold lines are used to create rigid subsections from the planar workpiece, and the remaining fold lines are used as the kinematic joints between these rigid subsections. Various rotation axes are achieved by shifting the relative location of the joint in the planar pattern, and thereby placing it adjacent to a different facet of the rigid subsection, labeled in the upper right figure A, B, or C. With the device consisting only of the single sheet of paper and suture thread for tendons, assembly simply consists of attaching the suture to the paper with knots, folding each segment into its three-dimensional form, and securing it in place, for example with adhesive, to ensure rigidity of link segments. The triangular prism shape is favored for its significant axial bending and torsional stiffness compared to other cross-sections. We also have another aspect to this research project, which has to do with the means of controlling this type of instrument manually. So we have a master-slave architecture with matched kinematics. In other words, the instrument that's inserted and the handle that's outside the patient are kinematically identical but may have different scaling. And we account for this size and motion scaling with pulleys such that you get a what you see is what you get motion with no mirroring, no lever effect that you would typically get when using laparoscopic instruments with straight, rigid shafts. So this shows a prototype that we've created, making an articulated instrument with just some heavy paper and thread. It takes just a few minutes to laser cut and a few more minutes to tie the suture thread to the instrument at the various attachment points. We use antagonistic tendons, which are routed inside the hollow prism until they reach to the actuated joint, at which point they emerge, and you can see in the photograph the thread that spans across articulation or a joint in order to have a moment arm across which to apply torque to actuate the instrument. So we simulated our instrument in MATLAB using a 3 degree of freedom articulation, 3 joints and 3 link segments, just like our prototype. There are 81 topological possibilities for how you could lay out such an instrument and orient the different joints, but really only 4 of these are useful and non-isomorphic. So we chose the one with the largest workspace, actually, and the workspace simulation is shown as the green blob in the lower right. This workspace also can be rotated about, translated along the trocar axis, or in other words, the axis along which you've inserted the instrument. And you can also then rotate about the insertion point with 2 additional degrees of freedom, giving the overall system 7 degrees of freedom. So 4 that are essentially passive in the way that you orient the system on the patient, and then 3 more that are actively articulated by moving the suture threads that drive the different joints of the articulations. In future work, we do need to add a business end, an instrument tip to this. There are origami-based forceps that have been developed by other research groups, so we could adopt something similar to that. We need to validate the properties and performance of this design relative to clinical requirements, and that includes the biocompatibility of materials. and we also need to build and test the scaling and control mechanism that was shown in the previous slide. I hope that you have enjoyed this presentation and learned a little bit about our work. I'd be happy to take questions. Thank you.